So good morning, everybody. Thank you for being here today again. So that's the last day of our spring school. We will begin with a presentation from Corberan, who is one of our foreign speaker and who helped us to organize financially the school. So thanks again. And so we will talk about LP-based method for solving routing problem. So I hope you will enjoy it.
Thank you very much, Caroline. Thanks to you for coming here today after the nice party we had yesterday. Too much wine and champagne, but very good. So I expect that you enjoy at least partially my talk. It is called linear programming-based methods for solving routing problems. In general, they are methods for solving any kind of combinatorial optimization problems, but I will focus on routing problems. I will introduce the methods, then I will apply it. Okay, I will show you some routing problems in which these methods have been applied. The first one is the famous traveling salesman problem that several speakers, among them Mark, told to us in this conference. And then I will show you some results we have obtained in 3 different R routing problems. The first one is a classical R routing problem called the stacker crane problem. And the second one is an R routing problem with profits. I will introduce briefly this family of problems. And the last one is is a generalization based on a particular and practical problem that was introduced by Bruce Golden several years ago. It's, I think it's interesting. I will not enter into many details, just show you the presentation, the definition of the problem, the practical application behind it, and the formulation very briefly, maybe some inequalities, but only focus. You must not care about the details. If you want to know more about details, you can ask to me, or you can consult some the slides or the papers in which they are based on. Just the flavor of the thing, and they are here just to show you that these methods, okay, as well as other methods, have been successful in solving combinatorial optimization problems. And at the end, since LP-based methods are polyhedral methods, they are based, as you will see, in the description of the polyhedron associated to the solutions of your problem, then I will give you some insights on the theory and even a couple of proofs that will show that are not so difficult as you can think. Okay, so let's start. And basically, the LP-based methods or polyhedral methods are based on the idea of formulate your integer problem as a linear program, and then using the methods, the powerful methods we have for solving linear programs. As I told you before, the effectiveness of these methods is based on a good description, a good understanding of the polyhedron associated to the solutions of your problem. Let's start. A combinatorial optimization problem or most routing problems can be formulated as minimize a linear objective function subject to certain conditions. X is the vector of decision variables, C is the vector of coefficients on the objective function, and the set of feasible solutions is denoted by S. Okay, given a problem like that, it is very natural to define the convex hull of our feasible solutions. This usually defines a polyhedron that we call convex hull of S. Since our feasible solutions I mean the vectors in S are associated with integer variables, with integer values of our variables, in that case, the convex hull has integer vertices. And then, since the objective function is linear, minimizing our original problem is equivalent to minimizing the same objective function, but on the convex hull of our solutions. And since it's well known that a polyhedron can be described as a set of linear inequalities, at least theoretically, since our problem can be formulated as minimizing the same objective linear function over conv of S, then theoretically it would be possible to solve our integer problem as a linear program. Okay, the idea is this is the set of our feasible solutions, S, the integer solutions inside this set. If we define, the red lines define the convex hull of our feasible solutions, then it is described by this set of linear inequalities, then solving our problem, that's its solution is an integer point, it can be solved if we would know this description of the convex hull. Solving the linear program on this polyhedron would produce an integer solution that will be the optimal solution to our problem. Unfortunately, complete linear descriptions of the convex hull of the feasible solutions of our problem is an NP-hard problem for any combinatorial NP-hard combinatorial optimization problem, and no convex hull, complete description is known for any of these problems. Anyway, although it will be not possible to know all the complete linear description of the convex hull of our problem, partial descriptions will be useful, are useful to solve our problem effectively. However, a problem we have to deal with is that even a partial description of the convex hull should have an exponential, used to have an exponential number of inequalities that of course cannot be fully added to our problem. For instance, in the traveling salesman problem, if you have an instance with 10 vertices, the number of feasible solutions for that problem is this number, and the number of different facets, I mean the inequalities you need to describe your convex hull, is more than 50,000 million. So you cannot put all of them for this small instance, you cannot add all of them to your linear program and then solve it by Cplex, Urobi, or whatever. Which is the alternative? The alternative is, since I cannot add all the linear inequalities that I know for my problem, then what I do is just add just a few. For instance, you know, this is an example of the traveling salesman problem taken from the web page, the TSP web page maintained by Bill Cook in Canada. You can access to it. Just put in TSP web page and you will find it. This is an instance with several cities from the Sahara, the old Spanish Sahara. You know that in the TSP you have two kinds of inequalities. The first one is that every node has to be incident with two edges, and the second, this is polynomial because you have an inequality for each vertex. And the other kind of inequalities are the subtour elimination constraints. The subtour elimination constraints, I'm looking for some, I'm sorry, I know that they are here, but maybe here. Cajones. There are several ways of formulating these inequalities, but a common one is that you have a subset of vertices of your problem, and then you say that you know that delta of S means the set of edges that are incident with vertex on S. That means if this is S, this is delta of S. Okay? So X of delta of S are the variables associated to the edges in delta of S. So our way of expressing the subtour elimination inequalities is saying that this should be greater than or equal to 2, because we have to traverse, we have to go from this part of the graph to another and coming back. Okay? So this is an inequality that should be added for any subset of vertices, and the number of subsets of vertices is exponential. So what we do is just adding just a few, or even none of them, and then we solve the linear program. Okay, we solve the linear program to minimize Cx in such a way that I is a vertex. So each vertex has to be incident with 2 edges. We just put these inequalities, we solve the linear program, and we obtain a solution like that, in which black edges in the drawing means that the value of associated variable is 1, and the red ones means 0.5. So the thing is that, as you can see, in this subset, for this subset of vertices, the number of, the sum, not the number of edges, because we are working with fractional variables. So the value of the variables associated to these edges here is 0.5 plus 0.5 is only 1 instead of being 2. So there is a subtour elimination inequality that is violated for this subset of vertices. The same happens here and so. So the idea is I cannot add all this family of inequalities, so I add just a few or none, and then I'm locating, or I am identifying those inequalities of this family that are not satisfied by the linear solution, and then I add them to the previous, to my linear program, and I solve again and again and again until all of them are satisfied. This is the way of avoiding this problem. The linear inequalities which are added to the LP at each iteration are called cutting planes, because they are cutting the fractional solution you have obtained in solving the previous linear program. The whole procedure that I explained very basically is a cutting plane algorithm, and has its origin in the work by Dantzig, Fulkerson and Johnson in '54 for the TSP, the instance that Mark showed us yesterday. Okay, this is the idea. Imagine that you are solving your LP. The optimal solution of your LP is here. Then what we have to find is a valid inequality cutting this point, but a valid inequality means that it should be satisfied by all the solutions of our problem. So on one hand of the inequality are all our solutions, and on the other hand the optimal solution of the LP we have solved. Okay, this is a valid inequality. This is not strictly correct. This is not a phase. This is a valid inequality inducing a phase of our convex hull, and this is another valid inequality inducing a facet of our convex hull. But I will present you these notions later at the end of the talk. Note that it is important to notice that this cutting plane approach needs for a method that identifies inequalities that are valid for our polyhedron but are violated by the current LP. What we have done here visually, I need a method to, given a linear programming solution, be able to identify if there are inequalities of this kind that are violated by our solution or there are not. Okay? So for each class or family of valid inequalities for our problem, we need to solve what is called separation problem. Given a class of valid inequalities, for instance, subtour elimination inequalities for the TSP, and a point that usually is the solution of our linear program, find an inequality in this class that is violated, by our solution, or prove that no such inequality exists. That means that all of them are satisfied. This separation problem can be solved by an exact or an heuristic method. It depends. Many times this separation problem is also NP-hard. And then we have to use heuristic algorithms in order to solve this problem. So a basic cutting plane algorithm scheme would be something like that. Consider an initial linear relaxation of our convex hull, and then solve it. Let this k its optimal solution, and then solve the separation problem for this optimal solution of the linear program and some classes of valid inequalities. The families of valid inequalities we know for our program. Then, if the optimal solution of the linear program is a solution of our problem, usually it is enough being integer, in that case, this is the optimal solution of our problem and we stop. Otherwise, if one or more valid inequalities violated by the linear solution are found, we add them to the linear program at hand, and then to create a strengthened one, we solve it, and so on. If no violated inequality is found, then we have to stop. And what happens if we stop here? If we stop here, can be because all the inequalities describing our convex hull are satisfied. We don't know all these inequalities describing convex hull, or we don't know how to find them, the violated ones. So in this case, we cannot follow. We don't know more valid inequalities that could be violated by our solution, or we don't know how to find some of them, although they exist. Then we have to stop, and the thing is that what we have obtained is a stronger lower bound in a minimization problem, and then we can go to a branch and bound or a branch and cut algorithm with a better bound and more possibilities for succeeding in solving our problem. The first cutting plane algorithm, as far as I know, in combinatorial optimization was proposed by Miliotis in '78 for the TSP, and the first branch and cut was used by Gretschel, Junger, and Reidneld for the linear ordering, although the name was introduced by Manfred Palberg and Giovanni Rinaldi for the TSP also. Okay, so this is basically the idea of how to use with a LP or polyhedral method for solving a combinatorial optimization problem. let me show you a few things on several routing problems in which this approach has been successful. I'll talk about routing problems. And as you know, node and routing problems are those related to the traversal of vertices or arcs of a graph. Among the node routing problems, the most famous ones are the traveling salesman problem and the CVRP that have been presented in this conference. And among the routing problems, maybe you have heard, most of you know the Chinese Postman problem, and several generalizations like the rural Postman problem, and also Christians talk about the capacitated routing problem, also Mark, that is the equivalent to the CVRP but into routing problems. I will introduce some of them for those of you that are not very familiar with them. Okay, let's start with the TSP. Just a few things. This is the definition that is taken from this web page I mentioned to you before at the University of Waterloo and is maintained by Bill Cook. Given a collection of cities and the cost of travel between each pair of them, the traveling salesman problem is to find the cheapest way of visiting all the cities and returning to your starting point. These guys, David Applegate, Bob Bixby, that was one of the creators of Cplex, and Dan Gurobi, he sold Cplex to IBM, and then he moved to, he created another company. Okay. Vasek Shavatal, and Bill Cook. They wrote a very nice book called The Traveling Salesman Problem, a Computational Study. And moreover, they have created a branch and cut algorithm called Concord that is able to everybody of you. The web page is very nice. You can find a lot of things, very funny things. And most of the things I'm presenting you are taken from this web page. Okay, just to give you an idea, also Mark talk about this. My information is in some way complementary of the Mark. It was nice. So these are the records of the sizes of TSPs that have been solved along the history. The first problem was the first instance was the instance of Dantzig, Fulkerson and Johnson of 49 cities in the States. Then for 20 years, this methodology was disappeared. Nobody tried working on that. Maybe because the linear programming methods or software was not so developed as our days. I don't know. But it was again in '77 when Martin Gressel used the same methodology, a cutting plane algorithm, for solving an instance of the TSP of 120 cities, at that time on Western Germany. So not the whole Germany, but of Western Germany. Also Crowder and Padberg solved this famous instance in 80s. Okay, Giovanni Rinaldi was with Manfred Parberg in New York working on that, and they made a very nice improvement on TSP algorithms until solving this instance. Then later came these four great guys, great in the sense of it's their contribution to the TSP, and they create Concord, the Concord branch and cut, and they were able to solve to optimality all these instances. Mark showed you or told you about an instance of all the cities of the world that they are trying to solve. These are the ones that have been solved to optimality. Let me tell you that most of you know what I'm telling, but what I will tell you, but just in case, that doesn't mean that we are able to solve all the TSP instance with, for instance, 2,000 vertices. They have been able to solve one instance of this size, but not all of them. This is the mystery of NP-hard problems. And the beauty, too. The difficulty and the beauty. Okay, I have chosen a different instance. This is a representation of the famous Mona Lisa by Leonardo da Vinci. This artist, Robert Bosch, created a TSP instance, just producing the painting, the drawing, by a solution of the TSP, like doing that. People don't know what to do with his time. Anyway, some others study these problems. Okay, just to tell you, this problem has not been solved to optimality. The best tour was obtained by this guy, Nagata, in 2009, and since that time nobody has given a better tour. Bill Cook has offered a price of $1,000 to any of you producing a better solution. The lower bound, this is the upper bound, a feasible solution. The lower bound, obtained by Concord in 2012, is very close, very, very close. They use a truncated branch and cut using an artificial upper bound, so not using the real one, an artificial upper bound of this value, and they could obtain this value for the lower bound. This bound was obtained using a net of many computers, and it is equivalent to use a machine for more than 11 years of computing time. Okay, not easy. No, I don't talk more about the TSP, just at the end I will show you how to prove the dimension of the TSP polyhedron, and you will see that's a very easy thing. Just at the end, when all of you will be tired, okay? Now I prefer to show you other problems in which this approach has been successful in the area of R routing. You know, the Chinese Postman problem consists of giving a graph. You have to find, this is a graph, in fact this is an undirected graph. The Chinese Postman problem consists of finding a tour, traversing at least once, a tour of minimal cost, traversing at least once all the edges of this graph. This is the famous Chinese Postman problem, and is the first R routing problem we know. It was proposed in 63, 64 by a Chinese mathematician, talking about a real problem of Postman. So this is the reason for the name. This problem can be solved in polynomial time, as all of you know, by using combinatorial methods, matching, shortest path, and minimum cost matching problem. It is also polynomially, it can be also solved in polynomial time if the graph is directed. But if the graph is mixed or windy, what we call windy means that it's an undirected graph, but the cost of going from I to J or vice versa can be different. In that case, the problem is NP-hard, becomes NP-hard. A generalization that I will introduce later of this problem is when you are not obliged to traverse all the edges of this graph, but only a subset. For instance, I have to find a tour traversing this edge, this edge, this edge, and this edge. This is called the rural, because of the neighborhoods reminding you the areas in which the postman has to visit in order to do its service. So this generalization in any kind of graph is simply hard. I will talk about this problem later. And the stacker crane is a particular case of this. The definition of the problem is to find the optimal sequence of movements for a crane or an arm that has to move objects, for example, containers, from a given origin to a given destination. This is an arm that has to take this piece from this position and has to move to that other position. Okay? Let me imagine that you have some containers. You have a container here that has to be taken to this position. Then I have to take another container here that has to be taken and translated to this place, and so on. And the crane can move everywhere in the graph. Okay? This problem can be modeled as an arc routing problem in the style of what I was mentioning before, can be modeled as a pickup and delivery problem. I pick up this and I deliver it in a different vertex, or like an asymmetric TSP. The people proposing the stacker crane problem, Frederickson, Hedge and Kim, in 78, define it as an arc routing problem on a mixed graph, where each link has associated a non-negative cost, and they've defined it as to find a minimum cost tour traversing at least once all the arcs defined by the movements of the crane. So imagine something like that. I have to transport a container from here to here, from here to here, and from here to here. And the crane can move along any of these edges in any direction. This is a mixed graph. I have to do this movement in this sense, following this arc, but I can move from here to here or vice versa. Okay? So a solution could be something like that. And I try to find the best tour traversing at least once all the arcs in red in the figure. Okay, for formulating it, we take the graph defined by the arcs corresponding to the crane movements is in general disconnected, and we call the sets of vertices associated to these connected components, we call them required sets. For these arcs that corresponds, I insist again, to mandatory traversals, we define the out degree of each vertex and the in degree, I mean the number of arcs that are leaving vertex I and the number of arcs that are entering at vertex I. And we use variables xij and xji representing the number of times the edges are these ones. I can traverse the edge 3, 4 in this sense on the opposite sense, and then I have two variables associated to each edge of the graph. The formulation is very simple, very, very simple. I just to minimize the traversal cost associated to the edges, to the movements of the crane, except those that are mandatory. We need to impose, these are connectivity inequalities, like subtour elimination constraints. In this case, take a look here. I have two components. I have to look for a tour that connects both things. And then I have to traverse this. Take a look that it differs from the subtour, the classical subtour inequalities, in which I say that this cut set has to be traversed twice. One, at least twice. One in each direction. And this is what these inequalities say. The number of times that I leave subset S of vertices should be at least once. I need to leave at least once and enter then at least once. Okay? The other equations are also the symmetry conditions, saying that if I enter 3 times at that vertex, I should leave it 3 times too. Flow conservation conditions or symmetry conditions. And the non-negativity and integrality of the problem. So this is a very basic formulation and very simple for the Stacker-Crane problem. As you can see, these equations are polynomial, one for each vertex, and the number of connectivity inequalities is exponential. So we will need some procedure for solving the separation problem associated to this family of inequalities. Okay, no more details. We have several families of valid inequalities for solving this problem, and this is the key for the success of our approach. We define an initial LP defined by a few connectivity inequalities. All the symmetry equations are several families of valid inequalities that we have proved that define facets of our polyhedron. Okay, with all this knowledge of the polyhedron, we implemented a branch and cut algorithm using this version of Cplex in 1 hour and this kind of machine. And just to give you an idea, we solved several not real problems, but problems or instances that were proposed by some Holland people from Holland that were working on real instances. They developed a heuristic for solving this problem and proposed these instances that look like that. This is an instance, a small one, that simulates the movement of containers for several places to other places. For instance, from here I have to move a container to this position, another container to this position, and so on. This is the kind of instances that they generated simulating, trying to imitate real problems. Okay, jobs is the name that they used for that, and means the number of movements for the crane transporting the containers. And just to show you that we were able to solve to optimality all these instances in this time. But a very important thing is that the gap 0 means the gap at the root node. So we were able to solve only with the cutting plane algorithm. We were able to solve most of these instances without branching or using branch and cut. A second set of instances, we wanted to know how far our algorithm could go, and then we generated more difficult instances on a grid like that. So this is a grid, and we define several movements for a supposed crane between vertices of this grid. Then we generated instances in grids of different sizes, up to 500 jobs, and the results were also good. We were not able to solve all the instances, all except 3. And in the 3 instances we couldn't solve in 1 hour of CPU time. The gap This is, we couldn't find even a feasible solution in this case, but in this case or in this case, but the gap is not far from the optimal solution. Let me tell you that we start without knowing any feasible solution. The knowledge of a feasible solution provided by a heuristic would help a lot to any of this, to our procedure. Okay, but how good is your algorithm? You have not compared with somebody else. In order to do that, we compared with a more general problem, with results obtained by Gilbert Laporte and another guy, Blais, in 2003, in a generalization of this problem. This is called the general routing problem that it has been mentioned here before. The general routing problem is called like that because it's a generalization of node and R routing problems, in the sense that you have to find a tour, of course, of minimum cost, visiting some vertices in the graph and traversing some arcs of the graph. So it's a mixed servicing nodes and arcs of a graph. And this is why we call it general routing problem. So the general routing problem on a directed graph consists on finding a minimal cost tour, visiting some of the vertices of the graph that we denote by VR, required vertices, and traversing all the arcs in the required arcs. Okay? Blais and Laporte transform these problems into asymmetric TSP problems. Let me tell you that since the research on node routing problems comes from many years ago, and much more people is working on node routing problems, the methods, heuristic and exact methods for node routing problems are more developed than those for R routing problems. So one way of solving R routing problems is transforming them into equivalent node routing problems and then using the methods, the existing and good methods for node routing problems. In this case, the idea was that you know that the asymmetric TSP problem is not a difficult problem. I mean, okay, that's it's an NP-hard problem, but it's easier to solve than the symmetric version, in the sense that the reason is that the linear relaxation that is related to the assignment problem is much better than the linear relaxation for the symmetric case. And a quite simple branch and bound algorithm using this assignment relaxation was introduced or was proposed by Paolo Todd and I don't know if Carpaneto and Todd in the early 90s or something like that, and it's a very successful algorithm. So these guys, what they did is to transform this problem into an asymmetric TSP and using the Carpaneto and Todd algorithm. They tried their approach in instances and up to 5,000 vertices and 50,000 arcs. Okay, you have here the characteristics of the instances, all of them with this number of vertices and this number of arcs. These are the number of required vertices we have to visit. Our tour has to visit these vertices and has to traverse these arcs, okay, in different proportions, in such a way that, for instance, in this case, we don't have vertices to visit, only arcs, so this is a pure R routing problem. On the opposite case, we have to visit only these vertices and no need to traverse any particular arc. So this is a pure node routing problem, okay? And in the other cases, you have a mix of both, so we are solving general routing problems. Okay, their transformation to the asymmetric TSP consists of transforming this into an asymmetric TSP of these nodes. They were working with instances of these nodes and solving the TSP on this graph, on this directed graph. Okay, they got very, very good computational results, taking into account that they solved that with a very slow machine of the time in a time limit of 5 minutes. What we got were, we were able to solve all the problems to optimality, all of them, in, in less than 1 minute of CPU, except the last one that, as I told you, is a pure node routing problem for which our method was not really prepared. Okay, this is just to show you that our method was also comparable with other approaches based on existing successful algorithms for node routing problems. The success of our algorithm, as I told you, consists of or is based on the families of valid inequalities we have found for the polyhedral description of the convex hull of our feasible solution. So it's important to do that kind of a study. Let me tell you a little bit about another kind of R-routing problems that's called the R-routing problems with profits. In this case, it's quite an easy problem we call the Orienteering R-routing problem. As you know, in most routing problems, the objective is to service a given set of customers. But in other problems, the objective is select some customers with maximum profit from a set of potential customers. Dominique, Pierre Dejean, and Michel Gendron, okay, there are a lot of papers dealing with this kind of problems, but many of them call the problems in a different way. So these guys tried to put some order in this family of problems, and they made a classification. They call routing problems with profits, and they classify them as price collecting problems, in which the objective, take a look first to the objective. The objective is to minimize the total cost. Of course, minimize the total cost, you have several customers that you can visit. If you visit them, you earn some profit. But if your idea is to minimize the traveling cost, then the best thing you can do is not leaving the depot. Unless you are obliged to get a minimum amount of profit. So in price collecting problems, the idea is to satisfy a minimum amount of profit collected, and with this idea, with this constraint, to minimize the total cost. On the other hand, in profitable problems, you want to maximize the difference between the collected profits and the routing costs. This is something more logical in the sense that you are putting both things in the objective function. The problem sometimes is that since you have traveling costs on the one hand and the profits on other, okay, you cannot minimize distance and maximize money. You have to put the same using the same unit in order to make the two objectives equivalent in magnitude, in the sense of magnitude. And finally, orienteering problems are those in which we try to maximize the collected profit. And again, if I have no restriction, looking for a tour maximizing the profit collected means they have to visit all the customers. and this is a TSP problem, or a capacitated vehicle routing problem, or so, unless we consider an upper bound on the cost, time, or length of our route. Okay? So I will focus on orienteering problems on the R routing side. We have been studying this problem and the version with several vehicles that is called team orienteering. The study was motivated by a real-life application that Claudia Archetti and Grazia Speranza knew from some company in Italy. The idea is, okay, the application was related to carriers that offer some transportation offers are put it into the web, and carriers try to win the auction in the sense of doing this job. Very basically, we will represent a transportation service by an arc, meaning that we have to reach a node with an empty track, and then this is a more simple problem. We have to go to a node with an empty track. We take all the load there, and then we move to another place, and we deliver all the load that we transport. Okay? The carrier, this is a particularity of the problem we study. The carrier has a set of regular customers that it has to service, and he or she looks for additional customers to fully use the traveling time of the vehicles. So, more or less, imagine that you have these are transportations. We have to transport something. The green arrows or arcs means regular customers. We have to do that for my customer that it's paying for me. That one, the green arcs. But there is the possibility of doing some more transports. The red arcs, they pay for me a profit. I win if I do this service. I earn something. But the problem is that I have a time limit for the vehicle or vehicles. Okay? So the thing would be to look for a route like that, servicing the required arcs corresponding to my regular customers and the ones that maximize my profit into my time limit. Okay, the problem was defined in a directed and strongly connected graph. These are the required arcs whose service is mandatory. These are the optional arcs, should be the optional arcs whose service is not mandatory but is profitable for me. This is the profit associated with each optional arc. This is the traveling time associated with each time, and I have a time limit for my route of Tmax. The orienteering and routing problem consists of finding a route, starting and ending at the depot, such that its cost or time is not greater than this amount. All the arcs in AR are serviced, are traversed, at least once, and the sum of the profits of the arcs of the profitable arcs is maximum. Then we define two kinds of variables. The X variable saying the number of times that the vehicle traversed any arc, and a variable Y saying that the vehicle is servicing this arc or not. Okay, the formulation is also quite simple. We maximize the profit collected associated to the profitable arcs. Again, the symmetry conditions on the vertices have to be satisfied. These are the connectivity inequalities, again, a little bit different, and I will explain you a little bit in a few seconds. We have to traverse necessarily the required arcs corresponding to my regular customers. We can, if we service this arc, this variable takes value 1, and then I have to traverse it. Otherwise, the value of this variable is 0, and then I have not the need to traverse the arc. The length or time of my route is less or equal than the max time, and the non-negativity and integrality inequalities. Let me say a couple of words. I don't know. Oh, it's here. Imagine that I have my depot is here, and then, okay, it was much better to put the depot here. And then I have, this is the depot, node 1, and then if I have an arc corresponding to a regular, to the order of a regular customer, that means that I necessarily have to come here in order to pick up the load here and deliver it here, then my vehicle should enter here. Okay? This is mandatory. But what happens if this arc is not corresponding to a regular customer, but a profitable arc that I may or not service? So in this case, I'm not obliged to enter in this set, only if I service this arc. So associated to this arc, I have an integer variable, ya, saying that if it takes value 1, then I'm servicing this, and then I have to enter here. Otherwise, if it takes value 0, then I don't need to enter here because I'm not servicing this arc. This is what this inequality says. It's an extension of the connectivity inequality. So for all profitable arcs, if I'm servicing it, then I have to go there to service it. Otherwise, this is 0, and the inequality says nothing. Okay? Well, we have studied the polyhedron associated to our feasible solutions. Again, as you can see, we do always the same thing. We have a formulation, we define the variables, we define the polyhedron associated to our canvas hull, and then we try to prove that they are facets or not. Anyway, following this reasoning and based on our knowledge of the polyhedron and the kind of valid inequalities we have found for the problem, we develop a branch and cut algorithm whose initial LP is that one, just using only a few of the connectivity inequalities. We have developed separation algorithms for these inequalities, one heuristic and one exact algorithm, and other families of valid inequalities. And we have run the code on instances with this number of vertices and this number of arcs. Just to show you as to feel the biggest ones. The biggest ones are instances with 2,000 vertices. This number of mandatory arcs to service, of profitable arcs that can be serviced or not, and we were able to solve instances, 64 out of 80 instances, in less than 1 hour of computing time. So again, take a look to the gap at the root node. The gap at the root node is very small, and this is the key for solving exactly the problem. Okay? So again, this is a problem. It was not very difficult. I'm showing you the ones in which we succeeded. There are others in which we were not able to solve large instances, but in this were not so difficult. Let me tell you. Dominique, just a few words about this method. Maybe some of you is thinking about this kind of branch and cut, cutting plane, branch and cut approaches to solving combinatorial optimization problems, and the column generation and branch and price methods for solving the same problems. Okay, the two approaches are very, very different, although they are complementary in my opinion. Cutting plane algorithms and branch and cut algorithms are very useful if, in routing problems, if you have just a few number of vehicles. In these instances, with 1, 2, 3, 4, until 5 vehicles, okay, it depends on the characteristics of your problem, but until this number of vehicles, these methods are very successful. Although they are not so successful when the number of vehicles is bigger. This is because of the symmetry that Emmanuel was talking about yesterday. There is a big symmetry between vehicles. So the thing is that I need both hands now. A vehicle is doing this, okay? So you impose valid inequalities because it is this vehicle is doing something that is not valid. It's violating an inequality of my problem, a valid inequality of my problem. Okay, then I impose this inequality. But what the linear programming software does is that then, okay, you are forbidding this for this vehicle, then this will be done by this other. And then by this other, and so you are playing and playing with one vehicle, the other, and so on. In this case, the column generation methods are more successful because they avoid that. Moreover, and this is an important thing, then because maybe you are thinking that column generation and branch and price methods are then more powerful than ours. On the other hand, if you have many vehicles, that is the good setting or the good kind of problems for column generation, if you have many vehicles, you have less customers per vehicle. So the routes are shorter, the subproblem that you have to solve is smaller, and then they succeed. But in the other case, when you have 1, 2, 3 vehicles, routes can be so long that then, okay, on the one hand, you have many more routes. So your set omega is larger, but moreover, the subproblems are much more difficult to be solved. The thing is that if you have the conclusion could be, I'm not claiming that it should be like that, but it could be that for a small number of vehicles, you can use this methodology, that it is simpler, in my opinion, than column generation, and column generation if the size of the fleet is bigger. And the best methods for R routing problems and node routing problems with several vehicles are the combination of both in what it is called branch, cut, and price, or branch, price, and cut, or whatever. You can permutate all the things. Okay, that's to break a little bit on this kind of problem. Let me introduce. I still have. You are not lucky. We still have 25 minutes. So no, just a few things more. And the last problem. This is an interesting problem. It's not a classical problem like the stacker crane. It's not belonging. It's not a mix of classical and new things like the routing problems with profits. This is based in a real application. We call it the generalized directed routing problem, but people know it better by close enough a routing problem. You will see why. Okay, as I told you, in most routing problems, the service to a given customer is modeled as the traversal of a given arc. I have to pick up the waste of a street, and then I have to traverse the street in order to take the load of the containers along this street, okay? But, imagine that this is a container, I have to traverse this arc, this arc, this arc, and this can be the solution to a classical arc routing problem like that. However, suppose, and this is a technology that is implemented in my city town in Valencia, and it is starting implemented in many other cities. The thing is that each meter, gas, electricity, water, has a device that transmit the measure that it has to a reader. Okay, there are two technologies. In my city, Valencia is a quite big city, but okay, the measures are taken from a central point. And then most of these meters are connected to this place. But in wide areas, you cannot connect every meter through wireless connection or an electrical connection or so to a office, and the technology is such that works like that. So the meter sends the measure that can be taken by a vehicle with a device if the vehicle is passing by inside a given distance of the meter. So the thing is that now for doing the service to read the meter, we don't need to traverse the street in which the meter is. For instance, the man that came to my home in order to take the measure of my meter, but you need only to traverse a close enough street. So, for instance, imagine we have these 4 meters, the red, green, blue, and orange, and I can read the measure of the meter red if I traverse any of the red arcs. Also, if the vehicle traverses any of the green arcs, then I can take the measure of meter green, and so on. So the problem is to find a tool that traverses at least once of the arcs that service customer green, blue, or so. That's the idea. So selecting some of this, a feasible solution would be to select an arc of each color and then to design a route traversing these arcs. This problem, okay, from the theoretical point of view, was proposed by Michael Drexel, and he was the one that defined this like a generalization of the directed rural person problem, and then he wrote to us to say that he was the first one working on this problem, and then he thought that we should put the name of this problem. He was right, and then we called it the generalized directed rural problem, following his first work on that. But we knew the problem through this paper by Bruce Golden at Ed Basel. They defined the problem for the perspective of its practical application, and they published this paper called Advances in Meta Readings, Heuristic Solution of the Close Enough, they call at that time, Traveling Salesman Problem. You know, as was my comment before, the perspective of the people working on node routing, even for an arc routing problem, the close enough traveling salesman problem, they now call the problem the close enough arc routing problem. Okay, and some French and Canadian people work on that because these guys made a heuristic approach to the problem, and these guys with André Langevin and Jacques Rousseau, propose a formulation, a branch and cut, and very good results. We try to do it a little bit better. This is a real-life instances. A real-life instance with 150,000 customers and 18 so on. This is the problem that Bruce Golden and others study, and then they propose a heuristic. They found some solutions, and they found that with respect to the solution that was implemented until then, they got this improvement if the device on the vehicle could read anything on a radius of 500 feet. Only 18% if the radius is of 350 feet. Okay. The problem can be defined in this way. Note that a customer is a subset of arcs, in the sense that if I traverse any of these arcs, I'm reading this meter, the red or the green or whatever, and then what we have to find is a route starting and ending at the depot, traversing at least in one arc in each of these subsets, and such that the route length be minimum. Okay, it generalizes several problems. I have this, you have the details. Again, the notation is similar. The formulation too. I put some details here in order to show you the way we approach these problems. We define the compass hull of all our solutions. We prove that this is a polyhedron. We find the dimension, and then for the inequalities in the formulation, we try to prove that they are facet inequalities. And for instance, let me show you, these are similar to the connectivity inequalities I presented you before. Let me tell you that these were the initial inequalities, connectivity inequalities. Then they can be improved. We noticed that they could be improved because we tried to prove that they were facets and they weren't. So that means that they are okay, or we are not able to do the proof, or they are better inequalities. These are better inequalities in some cases, and these are facet defining. That means that they are the best ones we can find. Unfortunately, in other occasions, they are not valid, but these are valid, but they are not violated for several fractional solutions, and we also found, trying to prove that they were facets, a similar or related family of inequalities that is much better. And they define facets. So, okay, and many other things. Let me show you the computational results. The branch and cut is really a little bit sophisticated in this case, but let me compare our results with those by Langevin, Rousseau, and others. Their machine, in these problems, their machine was slower than us. They were not able to solve all these instances. We were able of solving to optimality all of them. Maybe the reason could be the speed of our machine, but a more important measure, because the speed of both machines and the implementation cannot be compared. But what we can compare is the quality of the gaps obtained by their branch and their cutting plane algorithm and our cutting plane algorithm at the root node. And the improvement on the lower bound obtained at the root node of our algorithm with respect to the one by et al. Is of this kind. So this is a big improvement if you are trying to solve difficult problems with branch and bound. This is the success, the reason for the success of our algorithm. And this is based in which we use improved versions of some, okay, we use new kind of inequalities, of valid inequalities, but we use improved versions of their inequalities. And the reason was that we tried to prove that they were facets and they weren't. So we were looking for improvements of them and we got these better results. Again, okay, this is the number of cats we added. There are quite a few, and we have several more computational results, but they are not so important. Okay, just 10 minutes to present you a few things on polyhedral combinatorics, not only on routing problems and so on. Excuse me. You know, a polyhedron is a set of this form. It's a subset of is a set of vectors satisfying a set of linear inequalities. The dimension of a polyhedron, we say that this dimension is k if the maximum number of affinely independent points is k plus 1. So the dimension is the number of affinely independent points minus 1. Maybe some of you are thinking, why talking about affinely independent points? What it was? Why not talking about linearly independent and so on? I will show you why. This is just a technical reason. You know that mathematicians like that everything be correct, I mean, well-defined and well-structured. This is only this reason. Okay, suppose let's call A equal to the set, the existing set. Maybe we don't know it, but possibly there exists a set of equations that have to be satisfied by all our solutions. For instance, in the TSP, the equations are the degree equations. Every vertex have to be degree equal to 2. These are the ones we know. Maybe there are others. So one result means that, say that the dimension is the number of variables, the dimension of a polyhedron is the number of variables of your problem minus the rank, okay, the linear independent equations of the set you have. Okay? In the case of the TSP, as you will see, the dimension of the polyhedron associated with the TSP is the number of variables, that is the number of edges in the graph, minus cardinality of V, the number of vertices, because there are V, cardinality of V, equations, degree equations. The thing is clear. Let me again use my hands. Imagine we are working on this, the R to the 3, okay, in this space, and all the feasible solutions of your problem, you have 3 variables, okay? We are working here, you have 3 variables, and all your feasible solutions satisfy an equation. What does it mean that your points satisfy an equation? That means that they are in an hyperplane, in a plane in the space. So if all your points are in this plane, the dimension of your polyhedron at most will be 3 minus 1. Okay, so you have to reduce by 1 any of the equations that are satisfied by your solutions. Okay? You know that we say that a set of vectors are linearly independent if the solution to a linear combination of them is all the coefficients equal to 0. What means affinely independent? Affinely independent means that the unique solution to this linear combination and the condition that the sum of the coefficients be 0 is that its coefficient is 0. So they are related, but it's not the same condition. Obviously, this condition implies this, but not vice versa. So linear independence is stronger, implies a fine independence, but not vice versa. These vectors are affinely independent if you subtract one of them and what you obtain are linearly independent. Okay, there is a condition that says that if your polyhedron, forget about this, if your polyhedron is contained in a hyperplane that doesn't pass through the origin, so the origin of our space is here, if our polyhedron is in a hyperplane like this, then in affine independence and linear independence is exactly the same. But this is not really the case. This is the idea. Imagine that you have your polyhedron is here. Then this point and this point, these two points are affinely independent. Why? Because if I subtract, remember that two vectors are affinely independent if and only if I subtract any of them, and what I get is a linearly independent vector. Okay, so this I have to these points. x2 minus x1 is a vector that is obviously is the only one I have, is linearly independent, and therefore these 2 points are affinely independent. Okay, what about linear independence? x1 is this vector, x2 is this vector, these 2 vectors are also linearly independent. So in this case, in which my polyhedron is in a plane that doesn't pass through the origin, 2 affinely independent vectors, 2 linearly independent vectors, the number of affine and linear independent vectors is the same. But what happened if my polyhedron is in a plane that passes through the origin? Then the 2 points are again affinely independent because x2 minus x1 is a vector that is linearly independent. Both of them are affinely independent, but x1 and x2 are not linearly independent. So in this case, the number of affinely independent and linearly independent are different, and what happened? My polyhedron has dimension 1. So in this case, dimension 1 is the number of affinely independent and linearly independent minus 1, but in this case, no. In this case, is again the number of affinely independent vectors minus 1, but is exactly the number of linearly independent. So that means that for defining the dimension of the polyhedron, I should say something like the dimension is the number of linearly independent vectors if I have my polyhedron is an hyperplane. If not, then is this number plus 1. This is not nice. And then it's always the number of affinely independent vectors minus 1. Okay? This is the only reason for saying or working with such a exotic definition. Well, an inequality is a valid inequality if all the points of my polyhedron satisfy that. The points in my polyhedron that satisfy with equality and inequality is called a phase of the polyhedron. And it is proper if it's not empty and it's not the polyhedron itself. A phase is said to be a facet if its dimension is maximal. So it's the dimension of the polyhedron minus 1. Let me show you this. This is the same drawing I showed you. This is a sad valid inequality. It can be improved by many others. This is an inequality defining a phase because the points in my polyhedron satisfying it with equality. There are some points satisfying it with inequality, but its dimension, the dimension of this point, is not a unit less than the dimension of my polyhedron. However, this valid inequality intersected with my polyhedron has dimension 2 minus 1 is maximal with respect to the dimension of our polyhedron. So this defines a facet, and what all we need to describe our polyhedron are the facets of it. You have another example. Take a look that there is only one inequality defining this facet of our polyhedron, but there are many inequalities defining or inducing the same phase. Okay, this is another. There are two basic methods to prove that a given inequality is facet defining, but the first one, that's called the direct method, consists of proving that all the points that satisfy it and belong to the polyhedron have dimension 1 less. Okay, I think we are at this. Just let me to say that this last part can be useful, just showing one proof, an easy proof. The TSP polyhedron. The TSP, you know, that is defined on a complete graph. 2 minutes. Okay. The convex hull of the TSP tours, of all the feasible solutions to the TSP tours, is a polytope. That means it's a polyhedron that is bounded. There is a result that I need to prove the dimension of this polyhedron. The result says that, for instance, if you have a graph with an odd number of vertices, then you can decompose the set of edges of your graph into several disjoint tours. For instance, let's suppose that your graph has 5 vertices. Then your complete graph can be decomposed in 2 tours, T1 and T2, that are disjoint, and all of them produce your original graph. We will use this to prove the dimension. The dimension of the TSP polyhedron is the number of variables, that's the number of edges, minus the number of equations they satisfy, that in this case is the number of vertices. We'll do the proof for a graph with 6 vertices. So we have to prove in 6 vertices we have 15 edges. We have to prove that the dimension is 9. Okay. Consider the graph with only 5, although we will try to do the proof for the graph with 6. Start with the one with 5 vertices. We have 2 tours, 1, 2, 3, 4, 5, and 1, 3, 1, 3, 5, 2, 4, 1. Okay? For the external one, what we'll do is, this tour exists. What I will do is to remove this edge and to add 2 more edges to the 6th vertex to create a tour for the graph with 6 vertices. Let me show you. We have the tour that was drawn. The tour 1, 2, 3, 4, 5, 1. Okay? This tour is using all these edges. Okay, for the first tour in the graph with 5 vertices, I remove this edge and I add 2 edges, 1, 6, 2, 6. Then I remove this one and I will add the edge 2, 6, 5, 6 in this way. Okay? So obviously what we get are tours for the graph with 6 vertices. I do the same with the tour corresponding to this inner part. Okay? Exactly the same. Each time I remove one of these edges and add the 2 ones linking their extreme nodes to the end nodes to the vertex 6. Okay, then what we have is this matrix. This matrix is non-singular. That means that all rows are linearly independent. So that means that what we have are 10, 5, and 5, 10 tours for our problem defined on the graph with 6 vertices that are linearly independent. Okay, but this linearly means affinely independent or not, and this is the end. Is our polyhedron, is the TSP polyhedron on a hyperplane that passes through the origin or not? Is our polyhedron belongs to a hyperplane? And the answer is late for letting you to think. The answer is yes. All our tours have to satisfy that the number of edges it uses are n, is n. All your TSP solutions use n, you have n vertices, you have n edges. So the sum of the variables associated to your problem, the sum has to be equal to n. So all our solutions belongs to this hyperplane that should be equal to n, and of course it's not zero, the right-hand side, and doesn't pass through the origin. So in this case, the number of affinely and linearly independent tours is the same. So 10 linearly and therefore affinely independent tours, so the dimension is this number, -1. So we have proof that the dimension of this polyhedron is 1. This can be done for any value of n. It's not so difficult. But it's new for many of us, and we have to enter a little bit on this kind of work. But the thing is that you have to construct feasible solutions to your problem. In this case, just feasible solution, and construct the matrix associated, and then prove that they are linearly independent, or so on. And to prove that some valid inequality is a facet is just to prove the same, but the feasible solutions cannot be any one, only those that satisfy your valid inequality with equality, and then prove that the dimension is 1 less than the dimension. Okay, do you have a few more easy examples then, but we don't have time, so this is enough for today, so sorry, thank you very much.
Thank you, Ronald, for your presentation. That was clear for a problem not so easy, so thank you. Maybe we have some questions?
I just have a quick question. In some of the problem at the very beginning, you introduced this technique, and you say we need to solve the LP relaxation of the convex room. And sometimes we cannot get solution, just a feasible solution of the LP relaxation. So how can we manage in that case?
No idea. This is the kind of problems I don't study. I will think about it, but I don't guarantee any success on that. No idea. This is completely based on the solution of linear solution. If you have a feasible solution, you mean a feasible solution of the linear relaxation. Yeah, then I suppose you can do exactly the same, but the problem is that maybe you are cutting feasible solutions that are even far from the optimal linear relaxation, so maybe it will take to you many iterations of the cutting plane, and I think it's better not to use this because you have no guarantee to approach your convex hull.
Thanks. Any other question? Yeah.
So, did you get results about the polyhedron study and validate inequalities if you had some time windows constraints?
No, no. I'm not. Okay, what I don't know are valid inequalities involving, okay, facet-defining inequalities involving the variables associated with the time windows. What obviously people use, I think I've read a couple of papers, what they use are valid inequalities for the problem behind this. I mean, if you are solving the TSP with time windows, they use valid inequalities, facet-defining inequalities for the TSP, but they don't include the variables associated with time windows. The problem is, this is, okay, it's a good question. In the capacitated vehicle routing problem, as well as with time windows, the problem with the polyhedron is that sometimes a polyhedral study is not possible. But I don't claim that you need to find the facets of your polyhedron. Using good feasible, good valid inequalities is enough. In the capacitated vehicle routing problem, we have a real problem. Is that depending on the numbers, on the demands and the capacity of the vehicles, maybe the polyhedron is empty. I mean, imagine that you have three customers. Three customers, I'm talking about the capacitated vehicle routing problem that you know. Imagine that you have, imagine you have three customers and you have two vehicles. Your vehicles have capacity 10. Okay? What happens? Your problem has no solution. It's not possible to find two routes servicing the two customers. Okay? So your polyhedron, you have no solution, the polyhedron is empty. So how can you study? This happens also with the time windows. It depends on the numbers. And then it's not, the polyhedral approach is based on the properties of your solution. If your solutions depend on the particular numbers of your instance, then you cannot do nothing. You can work with valid inequalities, even with facets for the problem when you remove these inequalities, but you cannot define facets for the whole problem because your polyhedron maybe doesn't exist. This is a nice thing that I wanted to say. Thank you.
Maybe your last question? Yeah.
You talked about the cutting plane approaches for the TSP. At each iteration, we will have to add cuts to delete some subtours. I mean, the enumeration of all the subtours can be time-consuming, so generally we add 1 or 2 subtours only to eliminate, but is there any information about the quality of the subtours? Is it more useful to add small subtours or large subtours so that the convergence would be faster?
In the subtour elimination inequalities, this problem can be solved in polynomial time using network flow theory and so. But they are very fast heuristics. So they are very fast heuristics that are based on finding the connected components of a graph. So that means that we can identify the violated inequalities very, very quickly. And I think, okay, it depends on your instance because each instance manages differently, but if your instance is not too big, the idea is to add as much connectivity inequalities violated as you have found. Okay, this is the idea, and they are the better inequalities you can add for solving the TSP, the more powerful. So it has been studied the level of the contribution of the different families of valid inequalities to solve the TSP, and the best ones are these ones. Okay, I can hear you.
For the VRPs,
Yes?
for the TSP, it's very intuitive to add cuts for the subtool elimination, but
Yes?
for VRPs, it's not the only problem. So what are the kind of cuts that we can implement?
The problem with the VRP, you have also the subtool elimination constraints, but the main inequalities in that case are the capacity constraints. The capacity constraints. I mean the constraints for everybody. The constraints that say that the customers you are servicing, its demand should not exceed the capacity of the vehicle. Okay, like I was saying here, these inequalities. These inequalities cannot. Okay, what you have is they are also exponential in number, but because it depends to any subset of vertices, to any subset of customers, and only a small number of them, a relaxation of them, that is called the fractional capacity inequalities, can be identified in polynomial time. In fact, it is supposed, it is not proved, but it is supposed that identifying the separation problem for capacity inequalities is NP hard. So you cannot find them. But if your problem is small, and this is what we are doing with the CARP, also with Christian, what we are doing is that if the problem is small, you can solve the problem exactly, although theoretically in exponential time. But with a small number of vertices, you can do it. You can do it, and they are the more important ones in the capacitated vehicle routing problem. You have many more families, but these are the most important ones. Okay, thank you very much to all of you. You have been very patient with me.
Yeah, thanks again, Angel, and here are your present.
I thought that I would not receive it. Thank you very much.
Thank you. So for people who are watching us on live, we will come back in around 20 minutes. So thank you again, Angel, and see you in a few minutes with Kenneth Sorensen.